Hey, Friday you guys have a quiz. It's going to cover homeworks 6.1, 6.2, which was already due. If you want to see those videos, go back a week. And it's going to cover these two homeworks, 7 and 8. So I'll make a video for 7, I'll make a video for 8, and we'll talk more tomorrow about everything. But for now, let's go. Taking a look at homework 7, number 1, it says the following graph shows the derivative of f prime. Identify the intervals when f is increasing and decreasing. Include a justification. All right, so obviously the easiest way to get this question wrong is to think that you're looking at f and then to say that we're decreasing from negative infinity to negative 1. That's true, but that's true about f prime. And they're asking you to use f prime to come up with when f is increasing, decreasing. And we know that f, oops, not a great start. We know that f is increasing when f prime is positive. So you're literally just looking on this graph for when the derivative is positive, not when it's increasing or decreasing, just when the derivative is positive. And positive means just above the x-axis, so here and here and all of this also. So all this green stuff is where the original function f would be increasing, and of course f is decreasing when the derivative is negative, and the derivative is only negative here, the part where it dips below the x-axis. So that's it. That's the only thing we have to do for this question, is identify that stuff. Now on the quiz, I'm sure I'd have other questions for you, maybe like just who are the critical values of f. And the critical values of f would be the points where the derivative is 0. So it would be those 2 points right there, right? The x-intercepts. It's also the places where the derivative is undefined, but there aren't any points like that. This derivative function is defined everywhere. But if you were going to give me the critical values, you'd tell me negative 1.5 is 1 and negative 1/2 is 1. But as far as your increasing, decreasing intervals, you'll just say that f increases on two intervals, the interval that goes from negative infinity up to negative 1.5, and also the interval from negative 1/2 to infinity. And that means that our only decreasing interval is from negative 1/2 to, or negative 1.5 to negative 1/2. And it does say justify. So all you have to do to justify is say we increase on these intervals because f prime is positive there. And to justify why we decrease on this interval, just say because f prime is negative there. And that'll do it. That's all. So number 2 is more of the same. Again, just look for those increasing, decreasing intervals by looking for where the derivative is positive and negative. So I see the derivative positive here between negative 1 and 0, and then positive from 3 to infinity. So on those green intervals, we can say f is increasing on the 2 intervals that go from negative 1 to 0 and from 3 to infinity. And again, your only justification is to say because f prime is positive there. And we can say f is decreasing on these 2 intervals, the interval that goes from negative infinity to negative 1 and from 0 to 3. Because the derivative is negative there. And that's it for 2. Number 3 says for each function, find the intervals where it is increasing and decreasing and justify your conclusion. Construct a sign chart to help you organize the information, but do not use a calculator. So it's important to notice that this time we're given f. We're not given the derivative. This is f. So if we want to find out when f is increasing, we need to actually find the derivative. So that should be our first step, is actually taking the derivative, which will be 3x squared minus 12, Then we know that we can find our critical values by setting the derivative equal to 0 and solving. So to solve this, I'd factor out a 3 to be left with an x squared minus 4. And again, my writing tablet likes to try to turn 4s into 9s. But that's a 4, which means that on the next step I can factor that down to an x plus 2 and an x minus 2. And that tells me that my critical values are x equals -2 and also +2. And we should test those. Technically, we're supposed to go up to the original function and make sure these values are in this original function's domain. But this original function's domain is all real numbers. It doesn't have any restrictions at all. So these two critical values really are critical values. And again, technically, when you're hunting for critical values, you're supposed to also check for where the derivative is undefined. But the derivative is a quadratic function. Its domain is also all real numbers. So it doesn't have any places where it's undefined. So that doesn't add any new critical values for us. So all that means, if you picture a number line, and if you plop the critical values down on the number line, -2 and 2, that'll help you see how to build your sign chart, because we can see that on this number line we've got an interval of all the stuff less than -2, then we've got -2 itself, then we've got all the stuff between -2 and 2, then we've got +2 itself, and then all the stuff greater than 2. So I'm going to need 1, 2, 3, 4, 5 columns in my sign chart, and I always need 2 rows. So I'll draw myself a couple of rows, and I'll divide that into a couple of columns. The one for -2 can be kind of skinny, because all you got to do is fit in the -2. Then the one for 2 can be a little bit skinny. That's 2. But the other 3 rows are for whole entire intervals. So we want to show that we're coming up from -infinity all the way to -2. We want an interval that goes from -2 to 2. We want an interval that goes from 2 to infinity. And technically you might want another column. Just you might want to label that in this row we're talking about x's, and down in this row we're talking about the sign, S-I-G-N, not sine like sine, cosine, tangent, but sign like positive or negative. And so we're doing the sign of the derivative, f prime. And we know that at -2 the derivative is exactly 0. At 2 the derivative is exactly 0. But in these intervals it's got to be positive or negative. So to figure out whether we're positive or negative, just pick a number. Pick any number that's in this interval. Like you could pick -3, or you could pick -100 or -1,000,000. But the idea is we're evaluating this, remember? We're evaluating the derivative. So if I plugged in a very, very negative number, then I would get, well, I'd get 3. 3 doesn't really do anything. Then I would get something very negative plus 2. That would be negative. Then I'd get something very negative, take away 2. That would be a negative. So I've got a positive times a negative, which overall makes a positive. So that's my derivative there. Then pick a number between -2 and 0. May as well be 0, or sorry, pick a number between -2 and 2. Probably you'll pick 0. And then you get 3 times something positive times something negative. And 3 times something positive times something negative would give a negative. Then pick a number greater than 2, like 1,000,000, and you get 3 times something positive times something positive, which of course is something positive. So here's your completed sign chart. Now we can do what we're actually supposed to do, which is just give the intervals where we increase or decrease. So based on this, we now can see that the original function f increases whenever the derivative was positive. So it increases on these two intervals, -infinity to -2 and also 2 to infinity. But because the derivative is negative between -2 and 2, we decrease on the interval from -2 to 2. So our final answer, the only answer that we really needed to give, was that f of x increases on -infinity to -2 and 2 to infinity. And we are supposed to justify, so just include that bit about because f prime is positive there. and also f of x decreases on the interval from -2 to 2 because f prime of x is negative there. That's our final answer. So that's 3. Hopefully I can go through the other ones a little more quickly. If you guys understand how to do the derivative and factor and build a sign chart, then I'll go through it a little faster on the next few problems. So looking at 4, we know we still want to find the critical values. We still want to use those critical values to build a sign chart. Then we want to use the results of the sign chart to decide where we increase and decrease. So to find this derivative, I could just go right after it. I could just treat this as the two factors and use product rule, but in my humble opinion, it's smarter to distribute this and then differentiate the new function that we get. So I'm going to distribute and get an x cubed minus a 3x squared. Then I can just differentiate that using kind of simple product rule, or simple power rule, sorry. So the power rule says this will just be 3x squared minus 6x. And then from there, if I set that equal to 0, I'd want to factor out a 3x to be left with an x minus 2. And from there, I recognize that I've got two factors. So to figure out the values of x that make this function 0, I can just take each factor separately. And I can say that when 3x equals 0, that'll give me some solutions. And the only solution it gives me is 0. Then I can say that when x minus 2 equals 0, that gives me some solutions. And the only solution that gives me is positive 2. So it's looking like my critical values are 0 and 2. I do want to take those and make sure that they actually work in the original function though, and they do. If I plug in 0, I do get some answer back. It doesn't matter what answer I get as long as I get back a real answer rather than something non-real or something undefined. So 0 is good. And if I plug in 2 squared, something else, yeah, it works. So these are both my critical values. So it sounds like it's time to build myself a sign chart, and my sign chart's going to want to have a 0 in it and a 2 in it. It's going to want to have the interval that goes from 0 to 2, and it's going to want to have everything less than 0, and it's going to want to have everything bigger than 2. And then that should cover it. That's everything. So it's going to be another sign chart with 5 columns, 3 intervals and 2 critical values. And then down here, we got to find those signs. Of course, bearing in mind that, again, 0 was a 0 of the derivative, and 2 was a 0 of the derivative. So both of those are just zeros. And then I evaluate these intervals, and I'm going to go ahead and evaluate this version of the derivative, the one where I just have a 3x times an x minus 2, because in my opinion, those are nice simple expressions that are just being multiplied. So I can see that for a very large negative, I'll be getting something negative times something negative, which gives me a positive. And for something between 0 and 2, the 3x will be positive. But something less than 2 take away 2 will be a negative. And a positive times a negative will be negative. And then for something bigger than 2, I'll get a positive and a positive, which gives me a positive. So is that the exact same results as last time? Yeah, it is. We go plus, minus, plus, different intervals slightly, but basically the same result where we're going to be positive and therefore increasing on 2 different intervals, and we have a negative derivative, so we're decreasing on 1 interval, and then you just have to write it out again. So we'll again say, this time it's g, so don't say f, you can say g is increasing on negative infinity to 0 and 2 to infinity, because g prime is positive there, and g is decreasing on the interval from 0 to 2 because g prime is less than 0, meaning negative there. And that's it. So that purple text is ultimately what we want to give as our answer, but you need the blue sign chart to justify this answer, and you can't build the sign chart without finding the critical values, and you can't find the critical values without doing the derivative. So all of this work is necessary. Okay, this is 5. So for 5, we're looking at a function. We know that to find the critical values, we need the derivative. And this time, I really can't get around it. I absolutely must do the product rule. So the derivative of x squared is 2x. Then we leave e to the x alone. Then we add to that the derivative of, leave the x squared alone this time. And multiply that by the derivative of e to the x. But the derivative of e to the x is e to the x. So there's my derivative. Now, to set this equal to 0 and solve, I would want to factor out my common factor, which they have an x in common, and they have an e to the x in common also. So x e to the x is common. And if I factor that out, I'm left with a 2 plus just a single x. Now, a lot of people were looking at this and thinking, okay, this is 2 factors. And so I can take those 2 factors, set them equal to 0, and solve. But it's not 2 factors, it's 3, because the x e to the x, that can be separated too by multiplication, right? So really what we have here are 3 factors, and I'll take the first, and I'll go, okay, x equals 0, and there's a solution. I'll take the second one, e to the x, and I'll set that equal to 0, and that of course has no solution. And it has no solution for a couple reasons. Probably the easiest reason would be if you just remembered what e to the x looks like. And of course the graph of e to the x looks like a graph that has a horizontal asymptote at 0, and then the graph lives entirely above that asymptote. So if you're trying to find a place where this function hits the x-axis and equals 0, you're not going to find it, because the x-axis is its asymptote. So that's why there's no solution from that particular factor. Then you grab this third factor, the 2 plus x, set that equal to 0, and then it's pretty simple. You subtract 2 from both sides and you get negative 2. So I'm realizing now that all 3 of these problems in a row were just 0s and 2s. The first one was a negative 2 and a 2. The next one was a 0 and a positive 2. And this one now is a 0 with a negative 2. So it's all pretty repetitive, but at the same time pretty different. So now that we've got those critical values, we are supposed to check them back up here, don't forget. But if I plug in 0, 0 squared is a thing, and e to the 0 is a thing, so this is not extraneous, he's good. And if you plug in negative 2 can be squared, and you can raise e to a negative power, so this guy's not extraneous either. They're both good. So I would make myself another sign chart. It's going to be another one with 5 columns. We're going to want that first critical value right here, the negative 2. We're going to want the next critical value right here, 0. And then my 3 intervals would be negative infinity to negative 2, negative 2 to 0, and 0 to infinity. And again, if I were you, I would be evaluating this factored form. So think of the derivative as just an x times an e to the x times a 2 plus x. Because if you think about it like that, then for a very large negative, the x is certainly negative. The e to the x, though, even for a negative, we're still positive. We're still just a hair above the x-axis, right? So e to the x is still going to be positive for us. But 2 plus something very negative will be negative. And so a negative times a positive times a negative will be a positive for us. Negative 2 is, of course, giving 0. If we plug in here, let's say we're plugging in negative 1, then x is negative, but e to the x is still positive, and 2 plus a negative 1 is positive now. So that's a negative for us. And then if you plug in 0, you get 0. And if you plug in something very, very, very positive, you get a positive, and a positive. So we're positive, okay? So again, now that we've got those values, we can easily answer the question. And again, we'll say that f increases on negative infinity to negative 2. and 0 to infinity. Because f prime is positive there. And f decreases on only this middle interval, the one that goes from -2 to 0. Same old reason, we decrease on this interval because the derivative is negative there. All of this pretty repetitious. Hopefully you are understanding all these steps. What's 6 about? Okay, so 6 is largely more of the same, but it does involve a trigonometric function now. So that gives us a chance to make sure we remember how to handle those. So again, I don't think I'd take the derivative right away. I think I would go ahead and distribute the 12. It just feels a little cleaner to me to have 12 plus 12 cosine t, and then to try to take my derivative. So from here, the derivative would be, well, the derivative of 12 is 0. The derivative of cosine is negative sine, so the derivative of 12 cosine would be -12 times the sine of t. And technically we should chain rule out the derivative of the inside, but the derivative of the inside is just 1. Derivative of t is 1, so we don't have to worry about chain rule for this particular problem. But you do have to worry about knowing how to actually solve this when it's set equal to 0. And of course this 0 isn't doing anything, and I could even divide by the -12 right away to just get all the way down to sine of t equals 0. And this is one we've done before. Hopefully you guys remember that at this point you just want to picture a big old unit circle, and you just kind of think about where would sine equal 0. There's no algebraic step you can do to get the answer anymore. You just have to know when the sine of t is 0. And since we know that sine equals the y value, you just whip around the unit circle thinking about when does y equal 0. And y is of course 0 here in this position, and y is 0 again here. So these are the only two positions on the unit circle where sine of t would equal 0. So that means t could take on those values. So t could be a 0 degree angle, or a 0 radian angle, a pi radian angle, a 2 pi radian angle, a 3 pi radian angle, a 4 pi, etc., etc. We could even go backwards and go -pi and -2 pi, da 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 da. Well, that is until you recognize what it says up here. It says up here we only want to use the interval between 0 and 2 pi. And remember, the soft brackets mean we're not even including 0 and 2 pi. So anybody bigger than 2 pi is not included. 2 pi itself is not included. 0 is not included. So actually the only correct answer is this one angle right here. It's only that pi rotation. And that's it. So since that's our only critical value, we have kind of a simple sign chart to build. Our simple sign chart would have pi in the middle, and would just build a couple of intervals left to right. But again, we have to stick to these restrictions. So we're not going to do -infinity up to pi, we're just going to do 0 up to pi. And again, we won't do pi all the way to infinity, we'll do pi just up to 2 pi. So that's it. So now you might be wondering, well, how do I get the sign of my derivative? Well, who was our derivative? Wasn't our derivative this? The -12 times sine of t. Now that negative, because it's negative, matters a lot. Because if sine is positive, well, the negative is going to turn it negative. So we need to make sure we keep that -12 around. That's part of our derivative, and it's definitely going to change our sign. So we want -12 times sine of t. And now imagine plugging in some angle that was between 0 and pi. Well, if you think about it, 0 to pi, that's just a rotation around the top half of the unit circle. And if I'm on the top half, then what do you know about all your y values? Aren't your y values always positive up here? So that means sine of t on this interval is always positive. So no matter what value I pick in this interval, I'm getting a -12 times something that's positive. And the -12 times a positive will make us negative on that whole interval. Pi is, of course, giving us 0. And from pi to 2 pi, pi to 2 pi is us rotating across the bottom of the circle. Now we're going this way. We're going from pi to 2 pi. But still, it looks like all my y values are negative, 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 negative. So that means on this interval, we're getting negative 12 times something negative, and a negative times a negative is a positive. So there, I built myself a sign chart, and using that sign chart, I can now state with confidence that G decreases on 0 to pi, because G prime is negative there, and G increases on pi to 2 pi, because G prime is positive there. And that's that for 6. All right, 7. 7 is definitely kind of a change of gears, because all of a sudden, yes, you may use a calculator, but more importantly, all of a sudden, you're not given f anymore. You're just handed f prime, which is actually our derivative. So to answer this question about on what interval is f increasing, you would just want to figure out when is f positive or negative. Now, maybe I could do that by hand. Maybe I could think this through about when is my derivative positive. Maybe I could find the zeros. But it does say right here to go ahead and use a calculator, doesn't it? So let's do that. I happen to have a calculator right here. Or more to the point, right here. Then it's not in the way. Okay, so what happens if I move that? Nothing. Great. Okay, so obviously you want to enter the function, and you'll go into y1 to do that. Put parentheses around whatever's in your numerator, so it's x plus 3 e to the negative x. And that's close those parentheses, and then divide by parentheses x squared plus 0.8. Yeah, that looks fine. So now just press graph. And that graph, I don't love it. I don't know what window I'm on. Let me try zooming standard, zoom 6. Yeah, so if I zoom 6 back to a 10 by 10 by 10 window, then this looks pretty good. Looking at it, I definitely would assume that this just keeps on going up, 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 up as it leaves the window. And I'm assuming this guy stays asymptotic to the x-axis as we go. If you wanted to be super careful, then you could go further out on the x-axis. Go like way out to 100, to 120, and go very close to the x-axis. Just go -1 to 1 on the y-axis and press graph. And I can't exactly tell what the graph's doing, but I guess I could hit trace. And oh look, even way out here, we're still at positive y values. So for sure, it seems to me like we're asymptotic forever. We never dip down below the x-axis. And that's important. I'm going to hit zoom 6 again. Looking at this graph then, I'm ready to conclude that my derivative function is just always positive. So we can state now that since f prime of x is positive on the interval that goes all the way from -infinity to infinity, we can say that f increases on that interval from -infinity all the way to infinity. And that's it. By looking at the graph of this function, or of this derivative function, I saw that it was always positive. And that tells me that function f is always increasing. And that's it. So let's try 8. So 8's more of the same, just with a different function. So I'll pull out my calculator again. I'll go back to y equals. I'll clear the old function, and I'll type in the new one. Negative sign of x, close parentheses, minus x times the cosine of x, close parentheses. And I'll press graph, and no, I won't. I mean, I will. I'll press graph. But I see a whole hot mess. So notice that they're restricting us to a pretty narrow domain. I only want to see the part that goes from 0 to pi. So actually, go back into your window and tell x to only go from 0 to pi. As far as the y values, I don't know if that's good or not. Let's just hit graph and see what we see. Sure. I guess those y's are okay. And so what do you see? I see a graph that is negative at first and then positive later. Now it looks like I'm getting 0 right at y equals 2, but you can go to your table, and I've got my table set to ask. If you do table setup, I'm set to ask. We've done that a lot in class, so I think you guys know what I mean. But if I plug in 2, womp womp, that's not where the 0 is. So since I need that 0 exactly, the best way to find it is to go into the calc menu right above trace. So hit second, trace. And we're looking for the 0. 0 literally, it means the same thing as the x-intercept. Maybe not literally, but basically. So choose that option. And for your left bound, just be anywhere left of where you think it is. So I'll press enter. For the right bound, I'd want to be at like 2.5. I could scroll over to 2.5, but you can also literally just type in 2.5 and it'll jump there really quickly. And for your guess, well, I guess it's probably about 2-ish. You can just press 2 and go there immediately. And now I see that my 0 is not 2, it's 2.029. And again, I'm looking for precision here. You can't just say it's 2 because it's close to 2. You have to do math to figure out what it is exactly. The good news is the math you have to do isn't algebra. It's just pressing buttons on your calculator, and that's okay, and that's good enough. But if you say it's 2 when I'm expecting 2.029, you're obviously not getting full credit. So just make sure you know that f prime of x equals 0 when x equals 2.029. That's what we said, right? 2.029. Okay, so that means we can now give our intervals. Remember, well, you can still see the graph on the screen, actually. I can't see it on my screen, but you guys can tell that, yeah, you know what, since I just said all that, it does look like the graph is 0 at 0, but shouldn't I double check? Let's just go to the table. If you plug in 0, you do get 0. But I don't want you guys making assumptions. Maybe for just a split second. Maybe the graph was positive for just a split second before becoming negative, but no, it wasn't. So 0, yeah, so from 0 to that 2 number that we found, the derivative is negative, so the function will decrease. And then from that 2 number that we found out to the end of our interval being pi, that'll be the end of our increasing interval. So I'm ready just to write this out now. We can again say since f prime is positive. I guess I want to do the negative one first. So since f prime is negative on the interval that goes from 0 to 2.029, f decreases on that same interval, 0 to 2.029. And I can say this a little more efficiently. Let's say and f increases on 2.029 to pi because f prime is positive there. So there's our 2. We've got that thing nailed down. So that's 8. Let's do 9. And 9 is again more of the exact same thing. We're going to analyze whether the graph is increasing or decreasing by looking at its derivative, which was given right to us, so we just plug it in. I'm looking at a 1 over x minus e to the x times the sine of x. I'm not sure if I noticed that before. Alright, did I enter that correctly? I think so. It'll do this multiplication automatically before it does the subtraction, so I think we're good. I'm going to hit graph, and yeah, that doesn't match what I put on my answer key, so whoopsies. I don't think I saw the sine of x on my answer key, so you'll have to forgive me. Also, My window's bad because I'm using the same window from before. So make sure you change your window to go from 0 to 4. It's not a huge difference. We're currently going from 0 to 3.14, but make sure you change that to 4. Press graph, and I'm seeing a pretty complete picture here. But I do need these two zeros again. So to find those zeros, I could try to do it by hand, but it's definitely complicated. So don't. Just do the second calc and use option 2 for zeros. And just eyeballing this, it certainly looks like that 0 is at like 0.75. So for my left bound, I'm just going to hit 0 and just go all the way left to the y-axis. My right bound, 1.5 is safe, so I'll do 1.5. Enter. And my guess is, 0.75. Enter. And I'm getting that. So it's 0.727. And that's fine. So that's my first critical value because it's the x-intercept of the derivative. Now for the other one, I'll do it all again. I'll go second calc, option 2, 0. I want to hop over here. Again, you can scroll, but scrolling takes a while. So again, it looks like 3 is going to be to the left of our answer, and 3.5 will be to the right of it, and 3.2, it looks just as good a guess as anything. So there it is, 3.128 if we round up. All right, and again, from the graph that we were looking at, we saw the graph do something like this. I don't know what it was doing, but it went like that. And so based on this, again, we can see that between these two critical values, that's where the derivative is negative. So that's where the function will decrease. And to either side of those critical values, the derivative is positive, so that's where the function will increase. So we know that we can say that f increases on. Now again, don't say negative infinity all the way to this value, because again, we were restricted to starting from 0. So we'll say f increases on 0 up to this first critical value, 0.727. And we also increase on the interval that starts at 3.128. And we don't go all the way to infinity because we had this restriction that tells us to stop at 4. So at 4, there's like a hard end on this graph. It doesn't keep going. So we'll stop at 4. And again, justify your answer by saying because f prime is positive on those intervals. And then just say, and f decreases on the interval between those critical values, 0.727 to 3.128, because the derivative is negative there. That's 9. All right. So far, so good. Okay, so for number 10, we come to a word problem. And the main thing with word problems, of course, is interpreting them correctly. And so reading this, it says, the rate. And you might want to underline the word rate. You might want to grab a highlighter and highlight the word rate. You might want to get a rubber stamp loaded with orange ink and stamp a big star next to the word rate. Because they are telling you, and let me just move the calculator a little bit. They're telling you that this function m, that function m is the rate of change. So function m is a derivative. Like it or not, m is the derivative. And so they want us to make a conclusion about the amount of money. So it's almost like there's this other function, a of t, and a of t is the actual amount of money. But a prime of t would be the rate of change of the amount of money. And that's exactly what m of t is. So even though m of t is not marked with little prime notation, that guy is the derivative. So when we go to attack this problem, we'll still just bust out our calculator. We're not going to do it by hand. We'll go into y equals and we'll enter e. I guess you want to grab this e that's above the division sign because you don't want to be prompted for an exponent. We just want plain old e. So e divided by 2 is the base, and we're raising it to the power of t technically, but we'll use x, of course. Now I could hit graph, I guess, but I don't really care about anything except the value of my derivative when t is 5. So this already is my derivative, so I could go to my table and enter 5 and just see what I get. I get a positive 4 point blah blah blah. The other thing you could do is if you just want to evaluate the graph, go into the calc menu, and that's what number 1 does. It just does a value. If I chose number 1 and entered 5, then that'll give me a cursor on the graph, so I can see I'm on a positive part of the derivative for sure. I can see I'm above the x-axis, and I can see the y value too. But that's it. I'm now ready to say that because the derivative is positive when x is 5, the amount of money is increasing when x is 5. And that's it. That's all you got to say. So just say something like since m of 5 equals, and don't just say it's positive, give me the value of it too so that I know you've actually done that work, but 4.638. And you know what, it wouldn't kill you to use appropriate units as well. So what is this? Thousands of dollars per year. So you could either actually write out thousands of dollars per year, or let's just write it out. Thousands of dollars per year. But what would make more sense is to just actually multiply this by 1,000 and just call it 4,638. And now it's plain old dollars per year rather than thousands of dollars per year. But that's that. Now what's important about this number? Only that it's positive. So you might want to say, since this thing equals this number, which is positive, I know the amount of money is increasing when x equals 5. And I know that the calculator is in the way, so I'll move it. And then you can read my answer. But yeah, we're saying since m of 5 equals $4,638 per year, which is positive, I know that the amount of money is increasing when x is 5. So you're pointing out that we're definitely increasing at that time, and we're increasing at that time because the derivative is positive. But that's it. Easy peasy. And 11 is kind of the same deal, except if you read this carefully, it says the number of hairs. Does it say the rate of change of the hairs? It doesn't. It doesn't say Mr. Sullivan is losing hair at the rate of this function. So this time when they give you h of t, that is not the derivative. That is the number of hair follicles. So we'll have to approach this problem a little bit differently. This time, if I want to decide is the amount of hair increasing or decreasing at time 7, I don't want h of 7. H of 7 will tell me how many hair follicles the guy has. I want to know is the rate of change positive or negative. So I'm after h prime of 7. So how do you get that? Well, you'll still take out your calculator. We're still in sort of the calculator section of this worksheet. You'll still go to y equals and enter the function that was given, which is 500 times e to the negative t, which is really negative x. You can press graph, and this is what, standard window, zoom 6, 10 by 10 by 10, that's fine. So 7 is in this window. We could go second calc, value, choose option, or choose 7, and we can pretty clearly see we are on a part of the graph that's decreasing. So it's certainly clear that the answer here is that we're decreasing at 7 because this graph is decreasing, but we're supposed to answer based on the derivative. So how do you find the derivative here? Well, that's built into your calculator too. Hit second calc and look at option 6. It says dy dx, right? So choose option 6, and it's just going to prompt, well, it doesn't actually show anything, but we know that we want the derivative at 7, so just now type 7, and that's basically saying, okay, you want the derivative at 7? Great, you press enter. Now it goes to 7, and it still gives you the y value, but we want the derivative up here, and we now can see that the derivative is negative. It's kind of weird that the value is equal to the derivative there. That's strange. Or is it? That may just be a byproduct of the fact that this is an e function, but I don't think that's happening everywhere. That's a little weird. All right, I'm going to shut up about that anyway and just move on. I would still want you to justify your answer by telling me what the derivative is. So since the derivative is, I can't read it now that it's gone, negative 0.456. And again, wouldn't kill you to give me units. This would be what? Hair follicles per year? But again, we're now able to say, since h prime of x is negative when x equals 7, we know that h of x decreases when x equals 7. And h of x is the number of hair follicles, so we're basically concluding that when x is 7, the number of hair follicles is decreasing. And that's 11. What's the difference between 10 and 11? In number 10, you had to understand that the function you were given was the derivative. So you just evaluate that function, and if it's positive, then the original function was increasing. If it's negative, then the original function decreased. This function was the original function, so we had to actually find the derivative. And when we found that the derivative was negative, we could then conclude that the original function was decreasing. So kind of different. And then lastly, number 12, we've kind of seen a problem like this before. This is sort of two opposing rates. So just imagine you had a gutter on your house, and let's just picture the gutter as a random container. It doesn't matter. But basically what's happening is water is flowing in at a certain rate, and that rate is g of t. But then there's also kind of like a hole in the gutter or something. And so there's water being allowed to flow out at a rate of d of t. So if you think about it, if water is flowing in faster than it can drain out, then the amount of water in this gutter will rise. But if the water is flowing in slowly and draining out quickly, right, if it's draining out really, really fast, then this gutter will start to drain and the water level in the gutter will go down. Even though water is pouring in, water is leaving faster than it can come in. So the whole point of this question is essentially just to compare those two rates. Just find g of t and find d of t and see who's bigger. But a better way to think about that is probably to say, well, what if I just made a whole new function called, I don't know, w of t or something, meaning the water in the tank. And the rate of change of the water in the tank would be the rate of change of the water entering minus the rate of change of the water leaving. And now if this expression is positive, then it's positive because g of t is the bigger thing. Water is coming in too fast, and therefore the water level is rising. If this was ever negative, it would be because d of t is bigger than g of t, which means the water level is going out fast. That would mean our water level is going down and decreasing. So we've now defined kind of a new function such that this new function, when it's positive, is the water level rising, and this new function, when it's negative, is the water level going down. So again, we could do this a couple of ways. We're certainly expected to do it in our calculator though, so you're going to grab your calculator, which I guess I left turned on anyway. And you're going to enter the two functions, y equals, clear. I want 10 sine x squared over 30. Yeah, that's it. And then for y2, I want negative 0.02 x cubed right, and then plus 0.05 x squared, and then plus 0.87 x. Okay, and both of these functions are only defined on the interval from 0 to 8, so I'll go to my window and I'll set it to only go from 0 to 8. And I don't know, I'll trust that my y's are okay. If my y's aren't okay, I'll fix them. But those y's seem fine. I'm seeing all of the graphs. But basically, the only value I care about is right at 4. So honestly, the fastest way to do this, I would think, is to go to your table and just ask it what's going on at 4 and press enter. And there's your two rates of change. This first one in blue is the rate at which water is entering, and it's 5-ish. And the one in red is the rate that the water is leaving. So if I'm gaining water at a rate of 5 and losing water at a rate of 3, then I'm gaining water at a rate of about 2. So clearly the answer to this question is that the amount of water in the gutter is increasing because it has a positive rate of change. If we did G minus D when x was 4, we're getting 2.084, which is positive, which means the amount of water is increasing. And that would be your answer. So I guess I'll write that out if you need me to. But we'll say since, don't say g of t, we're going to do it concretely at 4. We'll say since g of 4 minus d of 4 is equal to the 5.028, I think it was 5.028 minus 3, that's 2.028, 028? 084, dang it. Okay, 084. So 5.084. So that equals 2.084. Again, wouldn't kill you to include units. These are cubic feet per hour. But since this rate of change equals this rate of change, and again, just stress, which is positive, the amount of water in the gutter is increasing at that time. So when x equals 4. Period. End of story. End of video. You can't see the bottom. You can't see that I wrote x equals 4, but now you can. All right. I hope this video helped you. Don't forget, if it did help you, you could tell me that tomorrow in class. You could say, hey, that video sure was helpful. Thanks for spending 53 minutes and 22 seconds making it. Okay, anyway, thanks, bye.